C'est bon. Hello. Hello everybody. How are you today? While we're waiting for like more people to join, please drop in the chat where you guys are, which country. This is my son Ethan. You want to say hi?
Hello.
He's a bit sick, so today he's at home with us. He's a master of binary, by the way. So whenever you have a question, we're gonna ask him, right? Like we're gonna have like to do a lot of computation around 2 to the power something. So like Ethan, what's 2 to the power 4?
16.
16? How old are you?
I'm 8.
How do you know that? It's crazy.
Yeah.
Nobody knows that at 8. Damn. What's 2 to the power 3? What's 2 to the power 3?
8.
8? Wow. Okay. Are you gonna join Holberton and ILX?
Yes.
Yes? ILX?
Yes.
Yeah, nice. All right. He's gonna be joining soon. Very soon. All right. Okay, you say bye to everybody.
Bye-bye.
All right. So, are you guys ready to do a little bit of bit manipulations? And I guess you are, because otherwise you wouldn't be there, right? So, where are we going to start? Where are you going to start? Should we start with the basics of how to count in binaries? Maybe we should start there, right? So maybe we're gonna do a little bit of whiteboarding while we're at the beginning of the session, because my whiteboard works at the beginning of the session and then my computer goes crazy, memory allocation and things like that, CPU usage, and then it's harder. So let's. Oh, all right. It's already buggy. No problem. We're gonna do this with our friend Excel. Okay. So let's start with that. So let's just say we have a number which is this one. So how do we do to translate that into a number that we do understand? We do understand base 10, right? The numbers we understand is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the base 10, and like, this is an example of a number of a base 10, but this is an example of a number of a base 2, right? And these are, of course, these are the numbers that we have in the base 2, only 0 and 1. So how do we translate that into a number that we do understand, because this is the base we are using every single day, right? So here we take this number and we're gonna go through it from the right to the left, okay? So what's the value of the first 1? So what's the value of the first one? The one that is like on the far right. Anybody? Yes, 1. In base 2 it's 1. In base 10 it's how much? 1, 2. Now what's the value of the second one? This one. What's the value in base 2? Yes, Danny. 2 to the power 1. Exactly. So that's 2. And what's the value in base 10? 2, right? But really it's this, right? What's the value of this number in base 2? 0 is going to be 0 all the time, right? And now, like, for the far left one, what's the value of the far left one? This one. What is this value? In base 2, obviously, it's this, right? But what's the value in base 10? Is it 16? Marcelo? Danny, is it 2 to the power 5? What's 2 to the power 5? Is it 16? 2 to the power 5? Two to the power 4? 2 to the power 5? What is it? Is it 2 to the power 4 or 2 to the power 5? So is it 32 or is it 16? Who votes 16? Who votes 32? Drop in the chat. Are you voting 16 or 32? Oh wow, it's 50-50, huh? So 50% of you guys think it's... Oh, what did I do? 50% of you guys thinks it's 2 to the power 5 and 60% thinks it's 2 to the power 4. Interesting. So because we're like software engineers, what is the number we start counting from? Is it 1 or 0? And I think that's, you know, that's why. Oh wow, 16, 32, 32, 16. Okay. So let's go back here. So here, we know it's like 2 to the power something, but we don't know like which one. I mean, some of you know, some of you are right, some of you are wrong. So let's decide. What's the value 1? It's 2 to the power what? One is 2 to the power 0. Yes. 1 is... And then 2 is 2 to the power 1, 2, 3, and 4. So this guy is going to be 2 to the power 4. And what's 2 to the power 4? Ethan told you before, 2 to the power 4 is 16. Yes, exactly. So 2 to the power 4 is 16. And now what you do is you add all those numbers to have the result. So this number equals sum of all of this up. So this is 19. Okay? Any question about this number 19? You can still hear Ethan? Good. We're going to ask him more questions later. $264? Third World Gaming? What is 264? You're moving from left to right and not right to left. This is not the way you count in binary. I'm moving from left to right because here I put the number from right to left. M. That's why. Okay? So 1, 1, 0, 0, 1. It's the reverse order. So now I can go this way. Does it make sense? Should we do like another example and like just like put it the same way? Okay, so let's do this one. So this one, we're gonna take the first bit this time this way, and so we're gonna go the other way. So that's, you know, everybody understands. Okay, so the power 2 here, we're gonna start from the right. So this is gonna be power 1, power 0, sorry, power 1, power 2, power 3, power 4, power 5. Okay, so like the base 10 value is gonna be 2 to the power 0 equals 1. 2 to the power, no, this is 0. 0 times 2 to the power 1, 0. This is 1 times 2 to the power 1, that's 2. This is 0 times 2 to the power 2, that's 0. This is 0 times 2 to the power 3, this is 0, right? This is 1 times 2 to the power 4. 2 to the power 4 is 16, okay? And now this is 1 times 2 to the power 5. 2 to the power 5 is 32. And now this number is the sum of all of this. And so this is 50. Yes, correct. Toyin, 50. Jacob. Good. Up, carrot equals 6. Third World Gaming, I don't know if you're like following us, so I'm gonna... Strange. Just start typing your favorite number. That's what we are doing. Okay, any question about this? Does counting from either left or right matters? Yes, it does. And it's the same for every base, right? So if you have like a base 10 number, you know, and like this is the base 10 number. If you count from, like if you interpret those values from left to right and from right to left, it's different, right? So like either it is like 123 or this is 321. Obviously this is 123. It's the same in binary. Okay? But you guys understand how we count in base 10, right? Do you? So how do we decompose like the 123 in base 10? Anyone? So in base 10, if this is the number in base 10, this is 1, 2, and 3. It's the same thing. What's the power? We start there, 0, 1, 2. But the base is 10, right? So this 3 is 3 times 10 to the power 0. 10 to the power 0, like any number to the power 0 is 1. So 1 times 3 equals 3. Okay? This 2 is 2 times 10 to the power 1. 10 to the power 1 is 10, so that's 20. And this one is 1 times 10 to the power 2. 10 to the power 2 is 100, so 100 times 1 is 100. And so this equals the sum of all of this. This is 123. Right? So basically, like the way we count in base 10, we just count the same way in base 2. But instead of like doing 10 to the power, because this is a base 10, we do 2 to the power. But exact same way of understanding the number and computing, right? And so why do you think we call it a base 10? Anyone? Why is the base that we're using every single day is called a base 10? Anyone wants to answer? Yeah, decimal, but why? Multiplier of 10? Yes, but why? Why 10? It has a total of 10 digits. Yes, actually it has a total of 10 symbols. Okay? So it has a total of 10 symbols. Yes, because numbers are like 0 to 9. Okay, so who can tell me what this is? What is this? I'm gonna highlight it in a different color. What is this? What did I put in this cell? Yeah, I put this, Onatola, but what is it exactly? Is it 9? So this is not exactly 9. This is a symbol representing the number 9. It's not exactly 9. It's very different. I could put this and this. I could say this is 9 in my base. This is a symbol representing 4, like 9 in a different base. Or it could be this. This could be 9 also in another base that I decide to create tomorrow, right? So, you know, maybe let's digress a little bit to have fun. Let's pretend we want to create a new base. We're going to create a new whole world together. You know, this is going to be the ALX world. And in the ALX world, we are base ALX. This is our base. Okay, and now we want to count everything using only this base. This base is ALX. Okay, so what is the number of symbols in this base? The number of symbols in this base is 3. So this is going to be a base 3. And we have A, we have L, and we have X. So we need to decide what are the values of these. In base 3, in our base 3 ALX, this is going to be the value of this. A translation of base 10 is going to be 0, 1, 2. So X equals to 2 in base 10, L equals to 1 in base 10, and A equals to 0 in base 10. If we want to translate that in base 2, this is going to be 0, 1, 10. You guys following? Okay. So now that we have our new world, we want to understand what, and like somebody like comes to visit us. You know, they don't understand our base. So we're gonna need to translate everything we tell them into base 10. Okay? So let's just say we have this number. Okay? So someone comes and, you know, I don't know, like they want to create a website and you tell them, hey, this is going to be the price per hour for me. This is going to be LXA. So they don't understand. So now you need to translate that into base 10. So let's go through it. A, L, X, A, L, X, A. So now we're going to put the power here. This power is 0, 1, 2, 3, 4, 5, 6. Okay? And now, the one thing we maybe want to add is exactly what's the position of each of those letters in our base. Okay? And this is going to help us. So now, just going to put everything in center. So now this is A. A equals the position of A in my base. The position of A in my base is 0. So this is 0 times my base. My base is 3 because there are 3 different symbols to the power the position. And that's 0. Okay? Now let's do the second one, X. X's position is 2. So that's 2 times my base, 3, to the power 1. The position of X in my number. Okay, so what's 2 times 3 to the power 1? That's 3, right? Who wants to do this, the next one? This one. Write in the chat exactly what it means and what's the value and how you compute it to translate that into the power, into the base 10. The resolution is fine. It's probably your network. So what should I write? So look at how I translated X and A. What should I write exactly? Okay, so it's the position of L. The position of L is 1. So it's 1 times 3 because this is the base to the power 2 because this is the position in my number. So, Emmanuel, you're the current champion. Who can tell me what we put in this column now? Oh no, wait. To the power of 2. Yes, that's this. 1 times. So 1 times 3 to the power 2, that's 9. So what about A now? What is A? What should I write here? Emmanuel, my champion. I'm waiting for you. 0 times 3 to the power 3. A 0 times 3 to the power 3. Yes, correct. So this is obviously 0. Now, what about X? What is X? is x. So x is, wait, who said it first? X is 2 times 3 to the power 4. Yes, this time Onatola wins. Nice. Right before Emmanuel. What's the next one? L. This is 162. So what is L? This one. It's gonna be 1 times 3 to the power 5. Yes, Hassan, you win. All right. And who can tell me what's A now? Zero times 3 to the power 6. Exactly. Right? Any question? So that's going to be 0. What's 3 to the power 5? You have something? Power. Base 3. Exponent 5. 230, 244, 43. And now the number in base 10 is equals to sum of all of this. So this is 417. Okay? How did we get 162 for x? So x, it's equals to 2, this is the position, times 3 to the power 4. Got it? Second calculation is wrong. Which one is it? This one? 2 times 3 to the power 4. 2 times 3 to the power 4. This one is wrong? 2 times 3 to the power 4. It looks good, no? The value of the second x from right is wrong. The second x from right, so this one? 2 times 3 to the power 1. Yes, that's 6. Correct. So that's 420. Column H. Got it, guys. Thank you very much. Why are we multiplying numbers? It's a question from Nathan. So right now we're trying to compute what is this number in base 10. So we have to take the position of those numbers inside both, to take into account the position of those numbers inside both the base here and in the number. Okay? So for instance, in column H here, we have x. right? The position of x in ALX, in the base ALX, is 2 because we start counting from 0. So 0, 1, 2. So that's the position. Okay? And then the position in the number is going to determine like what power are we going to raise the base to. All right? So now you can create your own base in your own world. And now that we know this, we just apply the same thing to the base 2. Base 2 is simply 0, 1. Okay? That's my base. So you have the 0 and you have the 1. Okay? So the position of 0 and 1 in the base are respectively 0 and 1. This is a base 2, right? So in base 2 we see 0, 1. And in base 10 the equivalent would be 0 and 1. Okay, and in base 3 ALX the equivalent would be A and L. Okay, so now if we want to translate this number, so 1, 1, 0, 0, 1. The position in the base is 1, 1, 0, 0, 1. The power now is going to be, you start from the far right, 0, 1, 2, 3, 4. Okay, so the base 10 equivalent is going to be the position of the symbol in the base, 1 times the base, 2 to the power 0. Any number to the power 0 is 1. 1 times 1 equals 1. Okay, obviously this is 0 and 0. Here, 1, position of 1 in base 2 is... Ezekiel, I saw your answer. Let me finish this and then I can get on it. So again, here we have this number, which is like this one. This is the second from the left. So the position of this symbol in the base is 1. So this is 1 times 2, the base, to the power 3. The position from the right of this symbol in the number we want to translate into base 10. Okay, so that's 1 times 2 to the power 3. 2 to the power 3 is 8, so that's 8. Same thing here. The symbol 1 is in position 1 in the base 2 that we're looking at. It is in the position 4 if you start from 0 from the right of this number. So this is going to be 1 times 2, the base, to the power 4. So this is 16. And this number in base 10 is going to be the sum of all of these. So this is going to be 25. How can you do without writing this down? Well, it's not easy. It's very easy with the number 10 because with the base 10 because we use it like all the time. But they've been like in the past, they've been like civilizations that do not use the base 10. And like their base is going to be their reference. You know, you've seen like 12, base 12, base 7, I think. And like in computer science, we use base 16, you know, many times also. Like it's very frequent because it's very useful, except, you know, specifically for bit manipulations also. So now, like going back to Ezekiel, Julian, why do you start counting from left to right? So I'm not sure exactly if I answered your question, probably because now you switch to another one. Like mental math, what's the shortcut? There's no shortcut. It's going to be really like, if you want to be very good at this, you have to, you have to practice a lot. Emmanuel, you don't understand why is the position changing for this new calculation? Not sure which one you're referring to. Can you be more specific? Royalty Timmy, YAL for base 3. I assume you're referring to this. And what I was saying is that this number is equivalent to this number in base 3. And it is equivalent to this number in base 10. So A is 0, L is 1, AL for 0 and 1. Okay, Japheth, you have a shortcut. Please share with us. Okay, so Ezekiel, why do you start counting from left to right? Reference to the ALX, ALAA? Why do you start counting from left to right? I mean, can you be a little bit more specific in the question? I'm not sure I understand the question. Because we start... So basically like here, I put this number in the same order right here. Right? And then the position starts of this, like start from the right to the left. So this is what's gonna give you the power. And then we do like exactly the same as what we did before. Why are we starting by finding the position of the digits? Powerful music. It's because this is what is going to give you the value inside the base. Because I could have a base 10, which is 1, 2, 3, 6, 5, 0 like this, right? And this base 10 is very different from the one that we are used to. This is the one we are used to. But 0 in this case equals 0. 0 in this case equals 7. Why? Because this is the position of this symbol inside the base. So here the position of 0 is 0. We start counting at 0. And here the position of 0 is 0, 1, 2, 3, 4, 5, 6, 7. So the value of 0 in this base 10 is 7. Okay? Got it. Good. This time around, you're counting from the left. Yes, Tony, the counting from the left is inside the base. Okay, so the base is the collection of symbols that represent your base and are going to represent all your values within this base. So within the base, you start counting from 0. Okay, and that's going to give you the value of each of the symbol in this base. So this is the base. Now, like when we have a number, we go the other way around, because the further on the left is the number, the more value it has. So the base to the power x starts on the right at 0, and then you go from there. Okay? What's the difference between position and power? Position is within the base. Power is linked to the position inside the number. Okay? So if I have this number, you want to have 0 is going to be, and the base is obviously like the one that we know of and we use like all the time. 0 is the value, right? And it's based on 0 is based on the position of this symbol inside our base. So in this case, it's position 0. So the value of the symbol 0, what we call 0, because we're used to it, is 0. And so this is 0 times 10, the number of symbols in my base. So it's base 10. So 10 to the power, the position of this number, which is 0 also. Yeah, maybe it's not the right example. Let's take 3. So 3, the position of 3 in my base is 0, 1, 2, 3. It's 3. So the value of the symbol, this symbol in my base, is 3. Okay? But this one is not equals to 3. This is equal to 30, right? Obviously. So in order to understand what is the value of this symbol inside this number, not inside the base, but inside this number, now I start counting from the right. So it's going to be 3, the position in my base, that gives me the value. So 3 times the base, there's 10 symbols, so it's 10. So 3 times 10 to the power, the position of 3 starting from the right and starting counting from 0. So 1. So it's 3 times 10 to the power 1, so that's 30. So 3 here equals 30 within this context. Does it make sense? Yes, Wallaby. This is exactly right. This is like counting the numbers, units, tens, hundreds, and thousands. What I'm trying to explain to you is like, how do we get to there? Okay? So that like anytime you're gonna like have to deal with any number in any base, you understand what it means and how to manipulate all of these. Okay, Martin. All right, I got the green light from Martin. It makes sense. So now let's get back to binaries. Do I need to go through another example of how you count in binaries? Yes, Simon, exactly. The position of 3 is 3 in what we're used to. That's correct. But for instance, like, the hexadecimal base, it's base 16, right? Because there are 16 symbols. And it's this, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, F. Okay? That's base 16. What is the value of B? What's the value of B? We don't use B in our system, right? The value of B is the position of B in my base. So the value of B is 10, 11, 12. Wait, 0, 1, 2, 3, 4, 5, 6, 7, 9, 9, 10, 11. The position of B, it's 11 in base 10, right? What's the value of F? F is the position of F in my base. So it's going to be 15. So now if I give you A, B, C, 4, A, B, C, 4, A, B, C, 4. So what's the position to give you the initial value? Position in the base of A is 10, of B is 11, of C is 12, of 4 is 4. Okay? Now the power is the position of these digits, these symbols, inside this number. Not inside the base, inside this number. And you start counting from the right, starting from 0. Okay? So now what's the value in base 10 of each of these? This is 4 times 16, because it's base 16, to the power 0. Any number any number to the power 0 is 1. So that's 4. Now C is 12 times the base. The base is 16 to the power 1, because the power is right here. Okay? And actually I can do this. This is the position in the base times the base, this is 16, to the power, the position in the number. Okay? And I do this. And this is my number. Okay? So now that you understand how you do that, you can take any base and understand it right away. Okay? I'm not saying you can compute everything in your head. I can't, you know. But you can like go into like a piece of paper and like write everything down so that you can understand. But essentially now you get how we actually use numbers. So powerfulness. So for the position, we start counting from the left and power from the right. The position in the base is from the left. The power in the number that you want to translate is from the right. Correct. Okay? Onatola, got it? Peter, you learned this since primary school? You knew how to count in any base? How do you know what base to use? Omolara, the base to use is the number of symbols inside the base. So in this case, this is the base that we call hexadecimal. So it's 16, but it's 0, 1, 2, 3. So the number of symbols here from 0 to F, you have like 16 different symbols. Okay? So that's how you know what is the base. In the binary, the base is 2, because you have only 0 and 1s. 0 is the first symbol and 1 is the second symbol. In the decimal, for decimal numbers, like the ones that we are used to every day, there's like 10 different symbols from 0 to 9. So it's base 10. Okay? Wisdom, you're confused? Sure. What is your question? So Godwin, is it possible for us to convert between bases without first converting to base 10? I guess it is, but like we're used to base 10, so it's easier for us to do that this way. Why is B not 4? Why is B not 4? So B, in this case, B is the position of B inside the base. So 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. The position of B here is 11. That's why it's 11 and not 4. So you can do, you can do like base 16 to base 2 right away, but you have to manipulate binaries. It's a little bit less easy for us to understand, and Excel is not going to be able to do the sum. So yes, the other base systems are not familiar to most of us. Correct. Now you're going to be able to like start being comfortable with base 2, hopefully very soon, and maybe the hexadecimal one too. It's very interesting, the hexadecimal. Okay. We're not the matrix? Not yet. We'll get there. Okay. It seems that most of you get it. No, why do we have base 10 value? I thought we were working in base 16. Yes, we were trying to convert this number into a number we understand. We understand base 10. So this number, ABC4, is actually 43,972. But this number in base 10 is the same as this number in the hexadecimal base. These are the exact same thing in terms of value they represent. Tony has a question. Why does the hexa always end in F? That is 16. That is 15. Yes, it's 15. It's this is the base, but like a number can end with any, any symbol. It doesn't have to end with the symbol F. Okay? But like since there are like 13 symbols and it starts at the value 0, the position starts at 0, F is 15 and not 16. Yeah, base 8 octal is something we're using a lot too. Okay. Why do we prefer to use base 2 on computer system? Because like like the physical entities that like is at the physical layer is like either switch on or off. So we have like two different states. So it's either 0 or 1. Okay. There's no formula in Excel to do this. I don't think so. Maybe I can do a quick Google, but to convert like from any base to any other base, you're gonna have to do your own macro. All right. Okay. Let's stop here. It's been an hour. Is the session recorded? Yes, it is recorded. So you're gonna have time to come back here and look at some examples. And like, please, like once you look at the video, like please add some comments underneath if you have any question. And I'm gonna do my best to answer as many as I can. Okay? All right. So now, should we do a little bit of exercises? Or should we go through another example of how to compute binary? And I'll translate binaries into numbers. Yeah, Martins, you can write a C function. Exactly. So Awo has a question. What if there are more than 16 symbols? No problem. Like you count the number of symbols and then it's your base. So we can have like this number, this base could be your base. This is like a perfectly fine base, right? And we can have like all of these symbols in a number. And now the way to interpret them is the same thing. You count the number of symbols here. This is the base. And then you do the same thing with the power thing. Okay? So Muligeta, that we're not yet in bit manipulations. Right now we're like looking at what is a number. So now that we know what is a number, we're going to be able to do that. Okay, let's see what can we start with. Oh, maybe we can start with this. Maybe we don't need it for the first exercise. Should we do this one? Write a function that converts a binary number to an unsigned int. So we give you a string. We are given a string. And we need to convert it into a number that is in base 10. Okay. So, oh, someone, okay, one more please. So look, we're gonna do another example while we're coding. So we do both at the same time. Sounds good? Okay, so, is this ready yet? So we're gonna be given a string like this one, and we need to convert this string into a number. Okay, into an unsigned integer. This is gonna take a base 10 number. Okay, so it's gonna be base 10, but this one is gonna be given us in base 2, but in a string. Okay, so we're not given like this number. We're gonna be given a string. So as a reminder, a string in C is the collection of characters that ends with a \0. So in memory, we're gonna find this the character 1. Then the character 1, then the character 0, then the character 1, then the character 0, then the character 0. Okay? So, because it's base 2, we're going to start the power, because with any base actually. We're going to start the power here. And so this is going to be 0 times 2 to the power 0, 0 times 2, oops, 2 to the power 0. Okay, this is going to be 0 times 2 to the power 1. This is going to be 1 times 2 to the power 2. This is going to be 0 times 2 to the power 3. This is going to be 1 times 2 to the power 4. This is going to be 1 times 2 to the power 5. Okay, so really this is like this times 2 to the power this. Okay, up. Okay, and at the end, this is the sum of all of this, so this number should be 52. All right. Okay, so this is what we need to end with once we are past this string. So how are we going to go about this? The string starts on the left. So because it starts on the left, we don't know how big the string is, right? So we're going to have a pointer that points to the first char of the string. So there are like different ways to go about this. Okay? Did I miss a digit? Yes, I did miss a digit. You're right. Okay. Okay. No, I did not. So we're gonna get a pointer that points to the first character of the string, right? Remember how pointers work now. So, and I'm sorry, like the whiteboard is not working, so it's still like configuring. Thank you, Microsoft. So the problem is, what is going to be the base, the power, right? We know this is base 2, so obviously, and we know like 1 is the value 1 because it's the position 1 in base 2. Okay? But what is going to be the power? Since we don't know how big the number is because we only point to the first character and we are not given the length of the string, we don't know what the power of this is. So there's different ways to go about it. We could say, if you want to do it exactly the way we just explained it, what we can do is that we can compute the string length of this so that we're going to know exactly which one we start with. Okay? Another way is we go at the end of the string to the last 0 with our pointer, and then we go back. So we can do exactly what we've done here. This is not the most elegant answer, but maybe we can try this one first. Okay? Because this is exactly the way we understand it right now. And maybe we can find a trick to, go faster later. So let us just focus on one way to do this, and then we see what is the best, maybe. So because we did this way, and then we go that way, we can say, okay, let's move our pointer to the end of the string. So that's step 1. Move to the end of the string. Okay, and we start with the last char. Okay, so here we're pointing to 1, then we move, pointing to 1, we move, we're pointing to 0, 0, 0, and then here we're going to have the \0. And then we know it's the end of the string. Okay, so we know we need to start here. So now we have this one, we're going to have a counter, which is going to be called power. We start at 0, and every time we're going to move back, we're going to increase this number, just like we did here. And then what we do is that we add this to the total sum. Okay? So let's go to the memory template. So we are given 1 1 0 1 0 0. So 1 1 0 1 0 0. Again, these are characters. Okay, so I take a shortcut, but this is a character. Okay, this is not a number. You remember? And here we have the \0. Okay, and what we are given is a pointer. So on a 64-bit machine, this is going to be a 8-bit long pointer. So I don't know, we're going to call it P. It's going to be pointing to a char. And in this example, what is going to be the value of P? It's going to be 23. This is the address of the first byte of what I'm pointing to. Whatever is what I'm pointing to, it's always the first byte address. Okay? So here I'm going to have P. So what I'm going to do is I'm going to move P until the end, until it goes to this one. Okay? So essentially, while P is not at the end, we want to increase the value of P. We want to move from one address to the other. So here we have address 23, it points to 1, we move it, it's 1, we move it, it's 0, we move it, it's 1, we move it, etc., etc., until we hit the \0, for instance. That's one way of doing so. Okay? And then we move back. We start with the power, with another variable, power0, right? And then we move until we get to the first number. Okay? So our example, we're going to move P. So P equals 23. And the value of 23 is the character 1. So we move P. P equals P plus 1. Now it's 24. What's at the memory address 24? The character 1. Remember, it's not a value, it's a character. Okay? So we do P equals P plus 1. Now it's 25. What is at the address 25? The character 0. So it's still not the end of the string. So we do the same thing. Now with 26. Here is now 1. 27. Now is 0. 28. 28 is the symbol 0. Now we go to the memory address 29, and this is the backslash 0. Boom. Okay. This looks a lot like a while loop, but we'll get there later. Now that I have my P pointing at the end, I can just go back. So now we are 28. The character, this is a char, right? The char is the char 0. How do you convert that into an integer? How do you convert a symbol that is supposed to be representing a number into its number? Do you know that? So I'm going to have to convert this char into an int. So this is char 0. I convert it into an int. It's 0. I need the power, which is going to be the position of, yeah, a to I. But a to I, there's like a, yeah, char minus the, yes, exactly. This is it. So let's go back. I need the power, right? So I'm here. We're going to start the variable power at 0, and then we're going to increment it all the time. So it's 0, and right now my sum is my previous sum, which starts at 0 because we initialize everything. Okay, so my previous sum, 0 plus 0 to the times 2, because this is base 2, to the power 0. So we're still at 0. Okay, now I do p equals p minus 1, and I also do, I need to increment the power, right? So now my address is 27. What's at the address 27? The character 0. You translate that into an integer. The power is 1. And the sum is 0, the previous sum, times 0, the value of the current symbol, times 2, because this is my base, to the power 1. That's 0. Okay? I put value here. Now I do the same thing. 26. 26 is 1. This is my symbol. What's the value of 1 in the base 2? It's 1. Now my power has been incremented by 1. It's now at 2. Okay. What's the value of this? It's 1 times 2, my base, to the power 2, my power. So that's 4. So now my sum is the previous sum plus the current value. So that's 4. And then you do that again. So now we are like position 25 in memory. I have another 0. Okay, the value is 0. The power is 3. The value is 0. And my sum is 4. I do this again. Now I'm at 24. At 24 I have 1. The value of the symbol 1 is 1 in base 2. The power has been incremented to 4. The value of this 1 in this number is 1 times 2 to the power 4. What's times 2 to the power 4? It is 16. So the sum is now the previous sum 4 plus the current value 16. So that's 20. Okay? And now I'll do it again. 23. Okay, and then at the memory address 23 I have 1, the symbol 1. So now my integer corresponding to that, the value of this character is 1, the power is 5. This is the position starting from the right of this number. Okay, the value of this 1 is 1 times 2 to the power of 5, so that's 32. So the current sum is 20 plus 32, this is 52. Yes, we will release the record video later, Mohammed. Okay, so my number is at the end 52. Got it? So, yes, Anthony, the session is going to be later, available later too. There's one thing that we're missing, because now I'm going to continue, right? So now I'm 22. 22 is like, it's not my number anymore. So it could be like anything. And then it's not going to work. So how do I know I need to stop? The way I'm going to do is like, I need to stop at the first number. The address of this first number has been given to me by the call to my function. So what I'm going to do is that I'm going to save this address so that when I hit it again, when I go back, then I stop and I know I stop. So before I move here my pointer, I'm going to save it to another variable, say s, like starts, and I'm going to do this loop basically until p is either less than s or p equals s, depending on how we code it. Okay? So powerful music. You're a bit confused with the int and value column. So int is the translation of inside the base 2, what is the value of this symbol. So remember, what is in the memory is a char. You cannot manipulate it as is because you want a number at the end. So you need to translate it into an integer. Okay? And that's why here you see the same thing, but this has different types. Okay? Then the value of this one inside the number, so this is this one, is not 1, right? Because it's on the position 2. So it's really the value of this one inside the number is 1 times 2 to the power 2, which is 4. Okay? Okay, no question. So I guess I'm going to start coding this. Okay, should we go to Emacs now and start coding? Are you guys still here? Omo Wale, can I also say that there is a null byte at the start of my string? No, that's not correct. There's only a null character at the end, a null byte at the end of your string, not at the beginning. So the only way to know that this is the first letter in your string is by, saving the address of it. To Vim, no. Come on, I don't want to have nightmares tonight. All right, let's try to code that now. So first I'm gonna go grab the main file. Okay. the name of the file? Main file is what? 0 main.c. Okay, and this is the main file. All right, we're gonna start first without doing this, probably, and then we want the 0 class. What's the name of the other file? Binary to uint. Okay, what's the prototype? The prototype is this one. Okay, so here I have the string, I have the pointer b that points to a char that we're not going to change. That's why there is this const before it, okay? And b points to the first character of my string. So if we, in our example, this one 0 1 1 0 1 0 0, okay? This is like in our example. So b now points to this first one, okay? What we said is that we want to move b until we hit the \0. So while b is not \0, I'm gonna move b plus plus. All right, so this is the equivalent to that, okay? So now I should be at the end of my string. I want to do b minus minus to come back to my first, my last digit. So this is now b points to 0. Okay. So this is the equivalent of what we said here, right there. And now b points to, my 0 right here. Okay. Now I need to have two other variables, the power, or maybe three if we want to, the power, the value, and the sum, and the current value of that. So we can use the same thing exactly. So I'm going to use an unsigned int, I can't call it int, so I'm going to call it I want in power. I want unsigned int. I can just use unsigned here too. Unsigned int value, and I need an unsigned int sum. Okay. Here I'm going to initialize everything. So I is going to be computed all the time. I don't need to initialize it. Power is going to be initialized to 0. Value is going to be computed all the time. I don't need to initialize it. And sum, I need to initialize it to 0. Now I'm going to start my loop. While b is less than some other pointer that we call start, then I'm going to move backwards. Okay, so I'm moving backwards. And while I'm moving backwards, I'm going to say, okay, my I equals what's at the address B minus this. So that's my number. Okay. Now I'm saying, okay, what's the value of this? The value is this value inside the base 2 times 2, because this is my base 2, to the power. So here we have like a problem, kind of, because we don't have a function that is giving you the power of a number, right? So we're gonna have to write something like some kind of function here, but it doesn't matter. So far we can you just write it this way, and then sum equals the sum plus this value, and at the end you just return the sum. Okay, and actually we're just gonna do what's our example? It's 110100 110100. Okay. Can't we do 2? No, I don't think this is gonna work. I don't think this is working in C. But if you want the proof, we can try to compile. So GCC 0 main 0 binary main.h. There's no main.h. So just like to show you, main.h I put the prototype here. S is undeclared, of course. So here we need to, before we move B, we need to initialize S, right? S equals P. Unsigned, what did I do? Unsigned, or is it? In 3, unseen, int I, unsigned here. Okay, S undeclared, so we need to declare S, char star S. Okay, P undeclared, char star, oh, it's B. Okay, it's okay, we're gonna call it P. Const qualifier from pointer target type. Ah, of course. Hop. B undeclared. While B. Oh, I used B. What? I used B and P. Wow, okay, I'm tired. Okay, and now like this, we know that it doesn't work. Okay, so now we need to create this function. So power 2, we're gonna call it. Okay, so how do we compute? And so we're gonna give it the power of 2, and then it's gonna give it back to us. So unsigned, unsigned int power 2, unsigned int p like power. Okay. All right. why you're preferring unsigned value is because like the prototype of the function is unsigned, so we need to return an unsigned int. This way we're going to be able to return like more numbers as long as they are like not signed. What is the difference between b minus 0 and b plus 0? We're only using this, so I'm not sure what the question is. Yes, Omowale, you can use left shifts if you want to. So do you want to do that? So we're going to return 2. No. We're going to return 1. Power. Can you do that? Power and the clouds. What? P. Okay, so if it is P is 0, should be 1, yeah. Okay. So now if we do this, it gives us 0. Okay, something's wrong, obviously. So what's going on? So I have passed this one, s equals b. B is not, okay, b plus plus, b minus, power 0, sum 0, while b is less than s. No, of course. While b is greater than s. Okay, it's not working. So what's wrong? While b is greater than s. No, we want equal to. I is what's pointed by b minus 0. The value is I times power 2 power. So let's see. Let's debug. Okay, so I don't think it works. Unsigned int, expect a matching unsigned int argument formats. But value is unsigned int, no? What's wrong here? Oh, I forgot to pass the value. S is not assigned? Did I miss S? No, S is assigned, it's right here, right? S equals B after B minus. No, like you have to assign S equals B at the very beginning, because at the beginning, B points to the first character of your string. And so you want to save this address, because then you're going to go backwards and back to S. Okay? Yes, I think Lexi, you got it. I did not increment it, the power. That's why. Okay. So now this is working. So we're supposed to find 52, right? That's what we said here. That should be 52. So we have a first cool version of this. And actually, you don't really need a function for that. I didn't think you would think about that. And so I wanted to first do like the 2 times 2 times 2 times 2 within a loop, and then go back to the bit manipulation. So here we can just like use that. Up. And we don't need this function. Okay. Are you guys coding along with me? You probably should not. You should like, focus on what I'm saying, understand everything, and then try to do it again once I'm done. Don't try to like just copy, because otherwise, like if you're doing this at the same time, you're gonna focus on your code and you're not gonna ask the questions like where you don't understand. So maybe you're gonna get like a good score, but then you don't understand anything. Again, those sessions are meant for you to understand how people think and how you should think about a problem set and how to solve it. It's not about scores. Okay? Okay, so Godwin, you used b minus 0 to convert the value to int. What is the difference between b minus 0 and b plus 0? Okay. So maybe like we want to understand why we're doing minus, and then it's going to give you the answer to why we don't do b plus 0. So if you look at the ASCII table, right here. If you look at the ASCII table here, so again, this is like the decimal like value in the ASCII table of this char. So column 2 and 4 are the one you want to look at. So the char, we're given a string, right? So we're gonna have a string of 0 and 1s. The ASCII value of 1 is 49. You want to convert a character into a number. If you take directly the character, you're going to manipulate 49, not 1. Okay? You want to convert the character 1 into its equivalent value in the base 10 system that we're using. Again, if you're using the character as is, the value is 49. 49 is what's in the memory. Because it's a char, it's interpreted as the char 1, but it's not the value 1, it's the value 49. It's the ASCII value of the symbol 1 in the ASCII table. So in order to convert 1 to the character 1 to the value 1, you subtract the ASCII value of 0, because we know that in the ASCII table, those numbers are in the right order. 0, 1, 2, 3, 4, 5. They are one after the other. So if you have the character 0 minus the value of the character 0, it's like 48 minus 48, then you're going to get 0. If you have like the character 5, 53 minus 48 is going to be the number 5, and so on and so forth. So that's why b points to a number. This number represents the ASCII value of the symbol it represents in the ASCII table. And because they are like one after the other, if you subtract the ASCII value of 0 to like any character that is a number, right? And this is like one of the checks we need to do a little bit later. As long as this is a number, then if you subtract the ASCII value of 0, then you're gonna get the number, the value number of this character. Does it make sense? So like maybe like you're referring to like, why don't we do like b plus 0? It's maybe like if you want to do the other way around. If you want to convert a number into like one digit number into its character in the ASCII table, you do 48, which is the 0 in quotes, simple quotes. It's 48. plus the number. So 48 plus 2 is 50. It's going to give you the character 2. Okay, in this case we have the character and we want to convert that into the number, and so we do a minus. Okay? Okay, makes sense now. Awesome. Yeah, you can subtract 48. It's the same thing. Because like 0 in quotes, in simple quotes, is 48. In this case, it's better to use like the quotes, 0 between quotes because of the context. It says the context and it says that you understand why you're using this. 48 is kind of, random. If you have like someone who does not understand exactly the ASCII value thing, then it's going to take them like a little bit more time to understand. So always think about someone who's going to come to your code in like 6 months and has to change it. Think about the intern once you're like a senior software engineer. Okay, so try to write things the easy way. The easy meaning as simple as possible for someone else to understand. Okay, make sense? So yes, star B is a character because B here is a pointer. It's a pointer to a char. So when you dereference B, so B is the address of what it points to, and since we say it's a pointer to a char, when you dereference B, when you dereference B, you get to a char. 0 is also a char, yes. So here you're doing a char minus a char. So the ASCII value minus an ASCII value, these are actually numbers in memory, right? And so it gives you a number that you store in I. And that's how you convert like the character, as long as it's it represents a 1 digit, into a number. Okay? So the one thing, this little look at the ASCII table is telling us is that like what happens if I put something like wait, what's happening? Okay, my computer is having a hard time. So what if we put like something in between here, like that? Now it's like we're gonna say like the character E minus the character value 0, and so it's gonna give you like a big number. But that's not right. That's not what we want. So one thing we want to check for is that we only have 0 and 1s here. And if we don't, then we should probably return something like error or something. If there's an issue, I think we should return 0. So took So we're going to do this only if it's a 0 or 1. But if it's not a 0 or 1, then we return 0. There's an error. We don't continue. So if B is different from 0 and B is different from 1, then we have a problem. And we will just return 0. So now if I do that, I return 0. So now I'm checking for errors. Okay, so now explaining, okay, Emmanuel, I saw your message. Can you explain the bit manipulation that we use for the power? So let's go here. So we're doing this, right? What does that mean? this means that you're going to shift all the bits to the left. The bits of a number to the left, okay? In this case, this is the number 1. So that's 1. So if you shift this by 1, then it's going to be 1, 0. If you shift this by 2 to the left, it's going to be 1, 0, 0. If you shift this by 3 to the right, it's going to be 1, 0, 0, 0. And because we're in base 2, anytime you shift the bits to the left, you actually multiply by 2. Right? Because now, like, what is the representation of this in base 10? Now this is 2. Now this is 4. Now this is 8. So it's 2 to the power 3, 2 to the power 2, 2 to the power 1. What if it's like power is 0? It's 2 to the power 0. 2 to the power 0 is 1. Does it make sense? Emmanuel, does it make sense? So while you're answering, powerful music, you're asking, so I is a char or an ASCII representation? In this case, I is an integer. Okay? When you do this, actually, in memory, this is a number. So the result of this is a number. The type is a char. What does that mean? It means that it's a number represented in 1 byte. Okay? This is an unsigned int. As long as this number is represented in more than 1 byte, you can assign a 1 byte integer to a multi-byte integer. I is not a char, I is an unsigned integer. Okay, Manuel, you got it? Awesome. So if we are, Emmanuel, you're asking, so if we are in base 3, it will be 1. No, it does not exist. Let me share that with you, with everyone. Emmanuel is asking, if we are in base 3, can we use this operator? And you can't, it does not exist. You only have the binary operator. Okay, and why so? Is because we are manipulating the memory here of the computer. And remember, it's 0 and 1s. Maybe later when we have computers with 3 different states, CPUs with 3 different states, then we're gonna have this 3 smaller than operator. But today it's only 2 states. So it's 0 and 1, and so there's only this, because you're manipulating the memory. So it doesn't make sense to have something else than the binary one. Okay, Japheth, it doesn't make sense. So guys, whenever something doesn't make sense, please remember we have a 30 seconds delay or something. And second, please elaborate. I can't help you if you just say it doesn't make sense. What didn't you understand? What do you want me to re-explain? Do you want me to give you an example? Please give me more details, otherwise I can't help you. Why the \0, Umar? So we have a \0 because in C, any strings ends with a \0 or should end with a \0. Okay? When we do b minus 0, the result is converted to the real number 48. then stored in variable I. Yes. Are we going to have access to this content? I joined too late to even ask questions. Yes. Okay. Now, have we thought about like every case and like is this the end of our code? What specific case haven't we accounted for that is going to make our program not run properly? Yes, Umar, I say strings, but the string in C, the string type does not exist, right? So what we have is a pointer to a char, and the string is a succession of char that ends with the null character. Can you explain the code from the top? Can you explain the code from the top? This one? So this code, we said that the way, there's like, again, like there's many different ways to solve for this one, and this one is not the most elegant one, but this is the one we understand, the one like we came up with together, okay? The solution we came up with together is that we understand how now we compute numbers and how we understand numbers, and we need to start using the power number, okay? And this depends on the position of where we at in the number, and this power starts at 0 at the end of at the last digit of the number, so the one on the right, okay? Because we are given this number in string fashion, right? We don't know how big the string is. We don't know how many digits we have. So if we start at the very beginning to compute this number, then the problem is we don't know what power is right now. Okay, Japheth, I saw one, power. I'm gonna explain that later. Just please stop spamming. Okay, so going back to my explanation, this is allowing us to go until the end of the string and to start with the last digit. So we can start with power 0. Okay? And here, we're going to then go backward. So we're going to start with the most right digit, and we're going to go back to the first one. Because we've lost the value of b, we don't know when to stop, where to stop. What is the first digit? So we save it here. We save the memory address of the first digit so that we can stop at the right time. Okay? So now, let's go back here. So the number 1 in memory is represented in, depends on the architecture, but on 64-bit machine, it's going to be like, it's going to be 4 bytes, 4 bytes. Okay, so really, like, it's the representation of this is okay. This is how this number is stored. Actually, not always, but like let's just like imagine this is this, because there's like big Indian and little Indian. This is like one of the advanced tasks. But let's just imagine this is the way it is stored, okay? In theory, this is the representation of this number with 4 bytes, okay? So now, like if you shift this number, like x time to the left, then the representation is going to be this one has moved 3 times, like all the bits are moving 3 times to the left. But like since everything else is 0, then like you don't see the difference, but all the bits are moving to the left. So 1, 2, 3. And then of course you still have the same number of bits in a byte. You replace the new ones with 0. Okay? And so this binary number now is the same as 1 times 2, 2, 3. Okay, so it's 2 to the power 3. Why? Because here the position of this 1 now is 0, 1, 2, 3. So it's 1 times 2 to the power 3. 1 times 2 to the power 3. It's 8. Okay? So it's the same thing as doing 1 times 2 times 2 times 2. Does it make sense now? Left shift operation to say 1 power and x power at the same time. Does this answer your question, Japheth? Powerful music says, makes sense a bit. Slight play on words. Okay. All right, should we take another one? Did make sense now. Okay, Umar. Awesome. Japheth. Okay, got it. Means you only work for base 2. Yes, it's only for base 2. The shift. All right, cool. We're good. Oh, Barry, you don't understand where the 8 comes from? Okay, so let me re-explain that one last time and maybe you can go back to the video later. So here the base is base 2, okay, in this number. This is like a binary representation of a number, okay? To convert that into base 10, sorry, we said that all the zeros are zeros and then like the ones are like the value 1 and you have to multiply this by the base to the power the position of this digit 1. You start from the right at 0. So 0, 1, 2, 3 is your position. Okay? So in base 10, this is like this number is 1 times 2 to the power 3, which is 8. All right, let's take another one. Okay. Which one should we take? The basic one or the advanced one? It's been 2 hours already. Like, I think half of you have dropped from the... Yeah, maybe not half, but like a lot of you have dropped already. Should we take, let me see. Yeah, it's kind of the same. Get bit. Maybe we should do the Indian. The Indianness. Do you want to do this one or like an easy one? What else do we have? Advanced. One more basic. I don't know if we're gonna have the time to do everything. Okay, let's do like one easy and we can do the advanced. I'm gonna probably going to have to go a little bit faster. Okay, so I'm gonna do this one like let's do like set bit. Okay, let's do set bit and then let's do Indianness. Okay, so let's do set bit. So set bit. So we want to set the bit at the position index. Okay. So set the bit at the position index. So okay, let's just say we have like this number and we want to set this one to 1. So this would be index 0, 1, 2, 3, 4, 8. Okay. Set bit at index 8 to 1. Okay, so the way you want to flip this is that basically you have 0 and you want to have a 1. What can we use to do that? If you have like only, like forget about the position, you want to set a bit from 0 to 1. And don't forget, if it's a 1, we still want this to be a 1. What can we use to do that from this table? What should I do next session, Tony? I don't understand. Like, remember, this is going to be recorded, so if you need to go to bed, you can always come back tomorrow to look at, you know, what we've done. So using like one of these, how can I set for sure 1 bit to like a 0 to 1? The tilde, Kirian. The pipe, powerful music. The or. Okay. Anyone else? No? The tilde? The or? Yeah. Peter, you got it. All right. So if I have this, the binary OR operator, and I do this, I get this. And if I do that, I get this. So with that, if I do whatever the bit is, or 1, I'm going to set the bit to 1 no matter what. Okay? So if I want to set the bit at position 8, what I can do is I can have my 1, I move it to the position that I want. So how many times do I move it? If it's an index, it starts at 0, so it's the index directly. Then I get 1, 2, 3, 4, 5, 6. Then I move, then I get this number. Oh, come on. Okay. And then I'm going to do this number, binary or this number, and then it's going to set this bit to 1. Okay? Does it make sense? So what we need to do to set a bit to 1 at position index, we have 1, we shift this index times, then you apply a binary OR, and then you set it to 1. Okay? So let's just write this down. Set bit to 1.c. bit to 1. So you have a number unsigned int n and an index int I. Let's call it index. Then you have, you want to return it, I guess. Unsigned int, terminal. Unsigned int, and then you simply return this number. Okay, and that's it, done. Any question? So powerful music, we are not doing exactly 0, 0, 0, 0, 0, 0, 0, 1 pipe 1. We're doing whatever number it is, but we don't care what number it is, right? This was just an example. We don't care what number it is. Like it is n in our case. It is represented in bits in memory, and we're just gonna like binary OR it with to set the bit to this number. If the bit at this position, at this index was already 1, it's still 1. And if it was 0, it's now 1. That's it. And the index stands for 8. The index now is a variable. In my example, right before, I used 8 as the index, but it could be anything, right? Maybe I want to like set the bit number 27. When do I teach assembly? Episode 2. When you guys vote for it. Like you guys were the one asking for this one. And like there's like so many things that we can do. But let's just focus on this session first. Clear for everybody? Should we move on to the advanced one? You get it, you get it, you get it? Okay. All right. Let's do a little InGen, big InGen. Okay. So who can tell me what's the difference between little and big InGen? And why is it called little and big? What's the difference between big and little InGen? Yes, powerful music. 1 will be moved to that index position, and then we binary OR it with the number so that we set it to 1, to the bits to 1. Okay, so what's the difference between big and little InGen? Anyone? Nobody? Are we using little endian or big endian usually? So, Omojola, you're saying big endian uses the first of 4 bytes, little uses the last of 4 bytes. You use like, in any case, you use the 4 bytes. Little stacks from the bottom while big stacks from the top. I'm not sure I understand what you mean, Martins. So let's see, like this is, yes, this is kind of the way like those bytes are represented in memory, but like what's the difference between little and big, and why do we call them little and big endian? Okay, while I'm waiting for the answer, let's see what is the endianness of my machine. Does anyone know a command that I can run on my Linux to understand like what endianness like it runs with? Yeah, at least this is the order of bytes, but what order is all the bytes like on little and big? Okay, Lexi, last byte stored first byte stored first. For which one? LS CPU, Alice. Yes, nice. Actually, I had to learn this command before, like to prep for this session. I didn't know about it. I'm impressed that you do. So, like, it's gonna give you like a lot of different things, but one of the things it's gonna give you LS CPU is the endianness. Just gonna grab it. Byte order on my machine, it's little endian. So Chagosium, it's not the amount of space they use. They use the exact same amount of space. Yes, Hossam. It sounds like you just copied and pasted it, right? So in the little endian, the numbers with the numbers are going to be stored like from the byte that has the littlest value to the biggest value, and the big endian like the biggest value to the lowest value. Okay, so let's just say we have this value FF0044RR. Then in little endian, in memory, it's going to be stored this way. And then big endian, it's going to be stored this way. Okay? So if I have this number, then if FF is stored first or R is stored last, then I know it's a big endian machine. And then if it's a little endian machine, then it's going to be R first and FF last. Oh, sorry. So again, like if I have this number, on a little endian machine, it's going to be stored this way. And on a big endian machine, the first byte is the heaviest one. So it's going to be stored that way. Okay? So the way to know if my number is stored one way or the other is to look at the first or the last byte. Okay? So for instance, if I had this number on a little and on a big. So this number, the hexadecimal representation is 0x00000001. So on the little, it's going to be stored this way. And on a big endian, it's going to be stored that way. Okay? So now if I have a number, does it work? Is it working? Okay. So if I have a number, the number 1, okay, and I store it in an integer. So on a 64-bit machine, an integer is 4 byte long, and these are my bytes, right? So if it's a little endian machine, then you're gonna have 1 here, then 0, 0, and 0. If it's a big endian machine, you're gonna have 0, 0, 0, 1. Okay? The LS CPU should work on Ubuntu daily. So if I have n, now if I have the address of n, the address of n here is 25, right? So if I look at what is at the address of n, at this byte, right? Then I'm going to find 1 in little endian machines, and I'm going to find 0 in big endian machines. Okay? So the way to do this is just to look at the first byte of the number. I mean, one way to do this. You could look at the last byte of the number too. So Jacob, why 0 before 1 in the 1 example in Excel? One, 0, 0 before 1. This one, I guess. Because like if this is an integer, it's going like no matter what the number is, you're gonna set all the bits of the 4 bytes to represent the value 1. Okay? So going back here, so the way to understand this is like to look at the first byte or the last byte, okay, and see if we have our number represented there or not. So what we're gonna do is that we're gonna take a pointer to n that points to something of size 1 byte. So what's the type in C? What is a type that is size 1? In C, what type is of size 1 byte? A char, yes, exactly. So if we have a pointer like C, and we make it point to the first byte of our int, and then we look at the value of C, then we're gonna know if it's 0 or 1, and depending on that, then we'll know if it's a big endian or a little endian. Okay? So how do we do this? We're gonna have a number. Okay? We're gonna take its address. That's the address. We're gonna cast it to C. Maybe we don't even need to do that, the casting. Okay? Oops. Now C points to the first byte of n, and basically if C equals 1, we're going to do n equals 1. Of course, we need to set it to a certain value so that we can compare it to what we want to check. So if C is 1, then it's a little Indian. And if C is 0, then it's a big Indian. Does it make sense? Okay, so now we just need to code that. Emax is Indian than C. So we say int equals int n, and we say n equals 1. We want a char star C, a pointer to a char. We say C equals the address of n. Probably is going to compile this way. Maybe not. Maybe we're going to get a warning. We'll see. And then we say if C equals, if what's pointed by C is what at this address equals 1, then it's little Indian. Otherwise it's big. Okay, we're gonna include, I forgot. Let's do it again. So I'm gonna write the program. It doesn't take anything as an argument. If everything goes well, I return 0. Okay, we know that we need a number n. Okay, we do n equals 1, and then we know that we need a pointer to a char C, and we do C is the address of n. Okay, the address of any multi-byte type is the address of the first byte. Okay, and so if now C points to the first byte of n, and now if C is 1, then we can printf. We know it's a little Indian, right? And otherwise, it's a big Indian. Okay? I'm going to include stdio for printf. And I'm going to GCC this. Assignment to char. Okay. So that's where we want to do this. All right. And it's a little Indian. Okay. So we have our number. We take the address of the first byte of this number. If it's 1, then it means that the first byte contains the smallest values of this number, and then it's a little Indian, and otherwise it's the big Indian. So little Indian for little numbers first, and big for big numbers first, stored in memory. Are you guys good with that? Yes. Ekarika, little Indian starts from the smallest values. So remember, like the smallest on the right, normally on the far right, like in our system. So if you have 123, the smallest are on the right, right? The 3 is less than the 2 because the 2 is 20 and the 1 is 100. So like the big values are like first on the left. So if you have 0, 0, 0, 0, 0, 0, 0, 0, etc. 1, then the smallest values are on the right. So if you start with 1, it means that you start with the smallest values, the one that has like the less weight. So if you start with, if you have a 1 as the first byte, it means that this is Little Indian. It does mean in Big Indian, small numbers stored first. No, it's the opposite, Beriket. In Big Indian, the big numbers are stored first. Okay? Okay, guys, so I guess no more questions. So I guess this is the end of our 2.5 hour session. So I'll see you next time, maybe next week. And I don't know if I'm going to do a poll or if I'm going to do like something like Python next week. We'll see. So good luck to everybody who's doing their shell project. This is a really cool one. You're going to learn a ton of things.